Bismillahirrahmanirrahim. In this video, I'm going to talk about the time series forecasting methods using Python. So I will start with the simple forecasting method, that is moving average method. Then I will jump to the exponential smoothing methods. Then we will discuss the ARIMA methods, that is auto-regressive integrated moving average. And then in the end, we will discuss the Facebook's profit library to forecast the time series. As you know that when we are talking about a time series forecasting methods, so there are four components. One is level, okay, another is a trend, another is a seasonality, and then we have a random variation, or you can say the error. But the important part is when we are talking about the level, that means we are saying that the entire data over the time is varying around the average value. Whereas in a trend, either we have the linear trend, mean that is the increasing trend, or a decreasing trend. Okay, it could be a exponential trend, it could be a damn trend. We will see that what is the exponential trend and what would be the damn trend in the next slide. Okay, then we have the seasonal components. So seasonal components mean either it could be the quarterly seasonal or monthly seasonal. So depending upon the time series, we have to check whether there is a seasonality exist or not. Okay, so while we are forecasting the time series, so these components are very important. Okay, remember that when we are saying the seasonality angle, so the seasonality or the trend, they may have the relationship of the additive or the multiplicative. So additive means that over the time they are behaving at a same pattern, whereas in a multiplicative way, over the time it is increasing. Okay, as you can see that here the magnitude is lesser compared to over here. Okay, so that means here is a multiplicative seasonality or the trend relationship, whereas here we have the additive perspective. So we have to check that whether the additive technique is appropriate for that particular time series or the multiplicative time series. So we have the multiple methods of the exponential smoothing methods are available. Like NN stands for, that means there is no trend, there is no seasonality in the time series. So that we are talking about. So this is a level approach. That means overall, with the passage of time, the data is moving against a constant value. Okay, so that means it is varying over the constant value. So that's why we are saying that is no trend, no seasonality. So here we can apply the simple exponential smoothing method. If we have a additive trend and then we have no seasonality, then we can apply Holt's method. So right now I'm talking about the linear trend method. So it could be a linear, it could be the exponential trend, or it could be a damn trend. So depending upon the situation, we will see whether for that particular time series linear trend is appropriate, or the exponential, or the damn. So we will try to implement all these trends, and then we will see which method is appropriate for the particular time series. Then we have the seasonality perspective. So here we have, let's say if I'm talking about this one, so that means I am saying that, so we have the damn trend, that is a multiplicative damn trend, and we have the multiplicative seasonality. So that means the in the end the forecasting method we are getting, so the trend is the damn trend, but the relationship of the seasonality is, that is the multiplicative. Okay, so that is the exponential smoothing method. So based on these, so we have written 15 models formula. That is, this is basically the simple exponential smoothing method. So this is whole linear trend method. This is additive Holt's linear trend method. Okay, similarly we have the damn trend perspective. Okay, this is for regarding the multiplicative perspective. So this is regarding additive, and this is regarding multiplicative angle. So this is basic. These are basically the formulas for the exponential smoothing method. So we will discuss how we can implement these models in the Python. Okay, and then we will, after discussing this one, we will discuss about the ARIMA models. And the model I will going to select based on the Akai information criteria, as well as you can say Akai information corrected criteria, and then the Bayesian criteria. So based on these three criteria, we will try to select the best forecasting method. Okay, so how we can select that? When we will compare the AIC, that is the Akai information criteria or the corrected or the Bayesian, which has the lesser, or you can say the minimum value of Akai information criteria, that would be considered as a best forecasting model for the prediction. So based on these criteria, we will select the best forecasting method. So let's start with how we can implement these forecasting method in the Python. So I will start first of all creating the the time series, and then we will try to implement the simple techniques, that is basically the moving average techniques. So for that, first of all, I'm basically calling a library pandas, okay, as well as matplotlib. Okay, then this is a magical line, that is every plot should be in a line. So after running this command, then I am saying that I have the data of annual data, that is basically oil production in Saudi Arabia from 1996 to 2007. Okay, so we have every year's data points are there. So I have used a list, and then I have defined a data in a variable called data. So this is basically a list where we have created a list of data points that is in the oil production in the Saudi Arabia. Okay, now we are going to indicate that. So this is basically the time series, right? It is starting from 1996 to 2007. So how we can create a time series using pandas? So I'm saying panda dot date underscore range. So that is, we are indicating the date range, starting year, ending year, and then we are indicating frequency A. So A is indicating this is the annual time series. Okay, so if we write down M, that would be considered, it is the monthly data points. Right now it's annually, so that's why we are indicating A. And then we are storing this time series into a variable called index. Okay, as you can see that this is the index that is indicating the 12 years data from starting from the last month of 1996 to 2007. And right now I'm checking the type of the index, that is indicating this is the pandas index date and time type of the variable. Okay, now in order to create the time series data, how we can use? So we can use the pandas series function, that is data where we have stored the data points. Okay, and then index where we have stored the dates. Okay, so using this series function, I am storing into a variable that is called as oil data. And once I am checking that, it is indicating that it's a pandas series data type. Okay. Now, if I'm writing down oil data, we can see that this is a time series data. So 1996 oil production, 1997 oil production, and so on. So, first of all, the better way is to draw these data points in a graphical form in order to check the data pattern. Okay, so how we can do that? First of all, using these two a line of code, I'm indicating the figure size, and then I'm indicating the style. So right now I'm using the ggplot style of graph. Okay, so after writing down the background as well as the size of the figure, now I am indicating that the oil data in which we have stored this data set dot plot. So I want to plot this one is equal to x's. So that is a variable name. So why I'm doing this one? Because I want to label the x-axis as well as y-axis. So in order to label the x-axis, I am saying ax dot. So that means the entire plot is in ax variable. So I'm saying that label that plot on the x-axis here, label that plot on a y-axis, write on oil millions of tons, and then we are saying PLT, that is basically the Matplotlib plot. Okay, dot show, so that means show us the graph, and in the end I am saying that print this particular line. This is indicating the oil production in Saudi Arabia from 1996 to 2007. So on x-axis we can see that the years, on y-axis we have the oil production, and this is basically the overall time series. So first of all, I'm going to apply on this particular time series the moving average method. Okay, so for moving average, we can use the variable in which we have stored the data, that is oil data dot rolling. Then we are saying bracket start. So this is rolling is a function. We are saying window is equal to 2. Okay, so that means take the two values. So right now, first two values and calculate the mean. Okay, it's up to you. You want to calculate the mean or the median, but whatever the average point you want to consider it. So right now I'm using is mean average value. So this is basically the average of first two numbers. Similarly, this would be the average of second position number and the third position number, and so on. So this is with respect to the rolling window 2. Okay, similarly now we are plotting this one. So in order to plot, so just we are writing down plt.plot, that is the name of the function, and then entire thing which we have used earlier, so this one. So this is right now we are getting the uh, moving average 2. Okay, now I'm plotting basically the actual data set as well as moving average with 2 years, simple moving average with 2 years, and then with the rolling window 3, that is 3-year moving average. Okay. And then in the end, we are saying the legend location 1, that is basically the right hand side. So if you write down 2 over here, so this legend would be appear on the left hand side. So if I run this command, so you can see that. Okay, so first of all, let me run this particular command, because with the help of this one we would be able to set the figure size. Okay, now I am going to run this one, and then this one. Okay, so this is the figure size is 1510. Okay, and then we can see that the red line is basically indicating the actual data points. Okay, the blue line is basically indicating the 2-year simple moving average, and then the third line is basically indicating the 3-year moving average data points. So these are basically the very simple techniques of finding the forecasting methods. Okay, so this is basically the average technique. Okay, whatever the last point is, you can consider that point is for the next period as well as the forecasted value. Now we are going to talk about the important forecasting method, which is the simple exponential smoothing models. So right now, first of all, I am going to apply the simple exponential smoothing method, which did very well even in the forecasting competitions. Okay, so in order to apply the simple exponential smoothing method, so I am calling a library that is from statsmodel.tsa.api. Okay, so this is the library, and for that I am calling a module TSA, that is a time series analysis, and then I am importing the methods, which is simple exponential smoothing method. Okay, that is exponential smoothing, simple exponential smoothing, as well as Holt. So we are calling basically these three different methods. Okay, so in order to apply the simple exponential smoothing method, so what I am going to do is I'm saying simple, so S is capital, similarly exp is capital, and smoothing S is capital, and then the name of the data, okay, where we want to fit the simple exponential smoothing method. Then I am saying dot fit, so that means it should be fit the simple exponential smoothing method. And for that, I am indicating, as we know that for the simple exponential smoothing, there is a one parameter which is alpha, which is a smoothing level. So I am indicating the smoothing level is 0.2. So I am giving by myself, okay, and then I am saying optimize is false. So based on alpha 0.2, provide me the forecasting value. So with the help of this one, so once we run this one and then this one, so this with the help of this one, it is fitting the simple exponential smoothing method with alpha is equal to 0.2 and storing into the fit one. Okay, then if I am saying that fit one dot tab. Okay, so I can see a list of you can say attributes. So here I want to check the fitted values. Okay, so if I run this one, so I can see that this is basically the fitted value. Okay, means you can see that is a forecasted value against the original data was this one. Let me show you the original data. So this is the original data, which is 446 point this one for 1997 for this one, and this is with the help of simple exponential smoothing method, right? Okay, now we are going to talk about what are the parameter values. So we can write down fit one again, dot tab. So we can say paras. Okay, that is basically provide us the parameters of the simple exponential smoothing method. So right now it is saying that we have used alpha is equal to 1. So because we are applying simple exponential smoothing, so that's why there is no slope parameter, no seasonal parameter, no damp parameter. And what's the initial value they have used, okay, right now from the stats model. Okay, then we are indicating that show us the parameter in a formatted form. Okay, so dot, you can select the paras underscore formatted. So it is showing me that what the value of alpha they have used. It is not optimized alpha. That is basically the user defined alpha value. So initial level, so they have what's the value they have used as an initial value, and then again it is not the optimum. So in order to check what's the Akai information criteria, Akai information criteria corrected and Bayesian information criteria value, as we have seen that uh, that model we will select which has the lesser, or you can say smaller value of Akai information criteria as well as Akai information corrected criteria as well as Bayesian information criteria. So once we run this, so for model 1, when we have used alpha is equal to 0.2, so we got these values. So we can't say over here anything. So we have to fit the multiple models, and then we will compare which model has the lesser value of a kind information criteria. Obviously, smaller the value of these one, better the model is. Okay. Similarly, we are going to use alpha 0.2 in order to predict next three values. So how we can do that? So I'm saying that fit one dot, then we are saying forecast 3. So fit one, where we have fitted the model, dot forecast 3. So next 3 years forecast it is providing us, and I'm storing into a variable that is f cast 1, and then I am showing this particular value. So this is the next 3-year forecasted value using simple exponential smoothing value when we have the alpha is equal to 0.2. Okay, similarly, I'm repeating this process again. Okay, but right now the alpha I'm using is 0.6. Okay, and the variable I'm using, that is fit2. So in fit1 variable, I have stored the simple exponential smoothing models results when alpha is equal to 0.2, and in fit2 I'm storing the simple exponential smoothing results when alpha is equal to 0.6. Similarly, I'm getting the information criteria as well as Bayesian information criteria. And thirdly, and the third model which I am going to apply regarding the simple exponential smoothing, that I am not giving anything. So in dot fit, I am giving nothing. Okay. So here, as I have earlier specified that the smoothing level use 0.6 or 0.2. But right now I'm saying calculate the stats model by yourself. Okay. So Python will calculate by itself and pick the optimum value. Okay, so with the help of this one, so we have find the optimum alpha value. So it will calculate by itself. So there is no need to mention that one. So I am storing this one into fit3 variable, and then again I am getting the information criteria. So now we have three models, and against each model we have the information criteria value, information criteria corrected, as well as a Bayesian. So in order to compare that, what I am trying to do is I am saying model 1 fit. So all the values are storing in this particular variable. Similarly for the model 2's variables values, model 3 variable values, and then I am creating a data frame, okay, where the index are basically AIC, that is this one. These are the indexes, okay, and the column names are model 1, model 2, model 3. And then against model 1, I am saying in this particular column, store the values of model 1 fit, which is basically AIC of the model 1, AIC C of model 1, and then BIC, that is Bayesian information criteria of model 1. Similarly for model 2, model 3. As you can see that from this particular model, the chi information criteria of model 3, which is optimum alpha, that was calculated by the Statsmodels library by itself, that is the best. Okay, so based on that, model 3 is the best model for this particular time series. So now we are going to use this particular model 3 in order to forecast the values. So that is fit 3 dot forecast next. So this is according to model 3. These are the forecasting value for the next 3 years. So in order to check what's the alpha value they have used, so we can use fit3, that is in which we have stored the optimum alpha value. Okay, that is the optimum, you can say exponential smoothing model. Then dot paras. So right now they have calculated the optimum alpha value, that is this one, and this is the initial value they have used. So you can also access these values using this particular command, that is fit3 dot paras, and then we can extract the particular element which is smoothing underscore level. So that is this one. So this is the optimum alpha value we have used. Now we are going to draw the graphical plot in order to check the original data. So right now I am plotting the original data, and then I am plotting the forecasted value as well as the fitted value. Okay, so the forecasted value is the future value and the fitted value is against the data points. Similarly, when alpha is equal to 6, forecasted value, the fitted value. When alpha is optimum, forecasted value and the fitted value. So here we have, now you can see that the blue line is basically the best model fit line, and this is the predicted prediction where we can get the forecasting value for the future of the oil production in Saudi Arabia. Okay, now we are going towards if we have the linear trend. Okay, so now we are going to apply the holds with the respect of linear trend as well as a dam trend and the exponential trend. So we can do that. For that, I'm using basically air pollution data. Okay, so this is the again list we have used, and we have stored this data in a data file. And then again, in order to convert into the time series. So first of all, based on this data set, I have created a date range that is starting from 1990. So this is 1990s air pollution, and this is 2005's air pollution. And again, frequencies A, and I'm creating a time series with the help of pandas dot series. So this is data, this is index, and we have stored into a variable air, and this is a data series. So first of all, let's draw this particular time series. So for that, I'm again using the Matplotlib plot library. So plt.plot. So this is the air in which we have stored the data, and we can clearly see that with the passage of time, the air pollution is increasing. So now we have to see that should we apply the Holt's linear trend, or should we apply Holt's exponential trend, or should we try the dam trend. For that, first of all, let's apply the linear trend. So for that, the function is hold air in which we have stored the variable, and in order to apply that linear trend or exponential trend, so there are two parameters. One is smoothing level, that is alpha. Another is beta, which is indicating basically the trend parameter. Because we are defining by ourselves, so that's why we are writing sound optimize is equal to false. So once we run this one, okay, so it will fit the Holt's linear trend method. So by default, it will select the linear trend, and again we can see that the fitted value gives this model. Okay, and then we are renaming this forecasting, the future forecasting value of the next 5 years, that is 5. Okay, so this is next 5 years forecast. Now let's apply, instead of linear trend, exponential trend. So the only new parameter would be added in the hold function, that is comma, exponential is equal to true. The rest of the things I have used the same. Okay, Similarly, how we can apply the damp trend, that is additive damp trend, that is damped is equal to true. So now the trend, instead of the exponential, we are applying the damp trend. Okay, so based on the damp trend, this is the forecasted value. So again, we have fitted the three models. One is linear and another is exponential, and the third one is a damp trend. Let's check the chi-information criteria in order to find out the best model against these three models. Okay, so from these three models, we have fit one chi-information criteria. Okay, this is against the linear trend, this is against the exponential trend, and this one against the damped trend. Okay, so again, I'm creating a Pandas series and I'm storing the values of this one. And based on this one, we can see that the damped trend model is the better one because the chi-information criteria as well as Bayesian information criteria's values are smaller than compared to the other one. So that means the third model is the best model, that is the damped trend time series is the best for this particular time series. So again, this is the original data series we are plotting. This is with linear trend. This is against exponential trend. Again, forecasted fitted value of the damped trend. And then we are saying the legend location is 2, that means shown on a left side. So the blue line is basically our the better model, which is a damped trend line, and this is our future forecasted value with the help of damped trend. Now I am going to apply the Holt-Winter method where we have the seasonality in the data. And the data I'm using, that is basically international visitor in Australia. Okay, so this is basically a quarterly data. And as you can see that again, I'm using from Pandas date range. I'm indicating the start, end, and the frequency where this particular quarter is starting, and we are converting into a time series data and then index. And after converting into the series, we are plotting it. Okay, so this is x-axis, we have a year, and y-axis we have the number of international visitors. Okay, so again, in order to apply different models, so I have applied 4 different models. Okay, that is Holt-Winter method. So the first model I am fitting that is exponential smoothing on the variable age USD, that is Australia number of visitors. Okay, the time seasonal period because it is a quarterly seasonality, so that's why I'm writing on 4. And as you know that we have discussed earlier that the trend as well as seasonality, they may have the additive relationship or they may have the multiplicative. So right now I'm saying the trend is additive and the seasonality is also additive, and select the optimum parameter value. So that means right now we have 3 parameters. One is level, that is alpha, another is trend, that is beta, and the third one would be gamma value, that would be the seasonality component indication. Okay, the second model I am fitting, that is trend is additive but seasonality is multiplicative. And next I am indicating that trend is additive, seasonality is additive, but the trend is not the linear but the damped trend. Okay, similarly you can apply the exponential as well. Next we are saying that trend is additive, seasonality is multiplicative, okay, damped trend. So right now we have fitted the 4 models, and then we are getting the parameter against the first model which we have fit. That as you can see that right now for this particular model they have used alpha 0.4 something, beta value, gamma values, and what is the initial level value, what is the initial slope value, and what are the seasonality index they have used. Okay, so in order to again check which model is better from these 4 models, so again we are comparing the parameters, that is basically chi-information criteria. So for that, first of all, in results variable, I'm creating a data frame where the index are alpha, okay, and then we have the beta, right? Then we have the gamma. So this is the gamma value. Similarly, we have the initial value of for the level, initial value for the trend, then sum of square of error, chi-information criteria, Bayesian information criteria, and the parameter value which we have selected from over here. That is smoothing level, then smoothing slope, then damping slope, and so on. Okay. So how we can create that one? That is with the help of this is with respect to the first model. So the parameter we will select from these paras plus I'm indicating fit1 SSC plus fit1 AIC kite formation criteria plus this one. So using this one, we can store all the values over here. So in order to select the best model, compare the AIC or a BIC value. So the model having the lesser value, that is right now model 1 is the best model, okay, where we have used basically the additive trend and additive seasonality, okay. So model 1 is best one. So right now we are drawing all the data points. So black line is actual data point. The red one is the our forecasted value because this is the best model among all the four ones, okay. Now let's apply, we have completed the exponential smoothing models. Now I am going to apply the ARIMA as well as ARIMA stand for basically auto-regressive integrated moving average, and then ARIMA with seasonality factor, that is basically seasonal auto-regressive integrated moving average. As you know that AR basically stands for auto-regressive, I is integrated, that is basically the difference component, MA is basically the moving average. So A are basically using the past data and there is a parameter is P, that is basically indicating how many previous data points we have, actual data point we have used in order to fit the AR. So that means we need to find out the order value. So that is basically the P. Okay, similarly, in order to create the stationary time series, because for ARIMA models, the time series must be in a stationary form. So if it is in a stationary form, then we can apply the ARIMA. So how we can convert any particular time series into a stationary? Either we can take the differences or either we can take the log of the series in order to convert it to the stationary form. And then MS stands for the moving average, and the parameter of the moving average is Q, that is basically indicating the order, where basically moving average is using the errors of the forecast in order to predict the future values. And then if we are talking about the seasonality, then there is a seasonal components of um, ARs, auto-regressive. Similarly, we have differences and moving average, and then we have to indicate what's the seasonal number of periods we are using as a seasonal value. Okay, so let's apply this model in order to get the clear picture. So for that, basically, first of all, I'm reading a data which is basically a retail sales data. So that is basically on a daily basis how many sales a particular store has. So first of all, I'm reading that data and storing into a variable called sales. And in order to check the first six numbers, or you can first data six data entries, and saying sales dot head in order to check the first six numbers. Okay, now because the index are basically 0 1 2 3 4, so in order to create the date as an index, so how we can do that? So I'm saying that sales ds is equal to to date time. Okay, that is sales ds. So with the help of this one, we would be able to create the index of the uh, that is basically the time, date and time would be become the index, as you can see over here. But here right now this second column with ds is not unnecessary. So how we can delete this one? So we can use the function sales dot drop ds x is equal to 1. So it will drop this value, and after dropping it, I'm plotting this sales. As you can see that, so there is a trend. Okay, it could be a linear trend, but it's an increasing trend, as well as there is a seasonality component. So for that, I'm basically, in order to check the seasonality or a trend, should we apply the simple ARIMA model or should we apply the ARIMA with the seasonality factor? But first of all, as we have discussed earlier, that for ARIMA models, the time series must be in a stationary form. So for that, from the stats model, basically I'm calling AD Fuller, that is basically augmented Dickey's Fuller test, in order to check whether the series is stationary or not. So first of all, call from the stats model this test, that is, or you can see the module. And then we are saying our null hypothesis is that data is not stationary, whereas alternative hypothesis is data is stationary. So we are saying AD Fuller, so that is basically augmented Dickey Fuller test, that sales in which we have stored the data dot file, where we have the actual sales data. Okay, so once we run this one, so as you can see that we have the p-value, that is this one, and this particular p-value is greater than the alpha value, which is 0.05. So if this is the condition, we will say accept H naught, or you can say fail to reject H naught. So that means data is not a stationary form. So how we can convert into the stationary? So they are saying that this particular test is that take the 15 values difference. Okay, so how we can do that? So that means we are converting the actual series into a stationary form. So how we can do that? First of all, I am calling a particular variable, that is sales.y, and then I'm taking the difference and plotting it. Okay, so right now we have converted this time series into a stationary time series. So that means after converting it, that means we can apply the ARIMA methods. Okay, so in order to apply the ARIMA models, so first of all, what we are going to do is we will apply this particular library, mean we will install this particular library. So if you are using a Conda in Anaconda distribution, so you can use this particular command. So you should go to start Anaconda and then Anaconda prompt. So you can just copy paste this particular command. Okay, this command, and then just press enter. So this is actually I have entered 2 times. So I have already installed this package, so there is no need to run. So if you haven't installed, just put this command in a command Anaconda prompt and press enter, and make sure your computer is connected with the internet. Okay, so it will start installing. Once it is installed, then we are calling from this library, that is auto_ARIMA. So that means there is no need to tell the parameters of the ARIMA. So it will find out the optimum parameter value. So what are the optimum parameter value? So let's discuss in the next line of code. So first of all, I'm calling this one, and then in a stepwise underscore model variable, I'm storing that auto-ARIMA. Okay, that means it will select the different parameters of the ARIMA automatically. And on which series we are going to apply, that is sales.y. So that is the data points on which we want to apply this different types of ARIMA. As we have discussed that in our auto-regressive integrated moving average, so AR, auto-regressive parameter is P. So we are saying start P from 1. So start checking from for P order 1, 2, 3, 4 up to so on. Okay, and select the optimum one, which is the best model. Similarly, for moving average parameter Q, start from 1 and select the best one. And we are also indicating the upper limit for P and Q. Okay, so that means maximum check up to 5, for moving average check up to 3. Okay, then we are indicating the seasonality factor as well, as we have seen earlier that so this particular time series there is a seasonality as well. Okay, so we are indicating, so right now because it's a daily data, so I'm indicating weekly seasonality. So you can also try for monthly seasonality or daily seasonality perspective. Okay, and then we are saying that this is basically the seasonal component. So we are saying start from 0, seasonal is equal to true. Okay, and these are the differences. This is basically the starting ARIMA's differences. This is regarding the seasonality component, and with the help of this particular trace is equal to true, so you can see the results of different models. So these are the different models. Okay, this is the first model, this is the second model, this is the third model, and so on. and against that we can get the value of K-information criteria as well as Bayesian information criteria. So one, it will take some time. So after this particular time, we get the result and we can print the stepwise model in which we have stored this entire, basically the ARIMA model. And then I'm saying dot AIC. So print the model having the smallest AIC, that is 6566. As you can see that 6566, that is this one. Okay, that is this one. So which means this model is the best model for this particular time series, where the order is p is equal to 2, d difference is 1, and then q is equal to 2, and the seasonality component p is equal to 2, difference is equal to 1 and 2, and how many number of period in the seasonality we have considered, that is weekly, which is 7. Okay, so now we are saying that fit this particular model, that is stepwise underscore model dot fit, and then sales dot y is equal to model. So we have, after fitting this, storing into the model variable, and then I'm getting the model summary. Okay, so once we are getting, so as you can see that this is ARIMA model with seasonality component. This is basically the ARIMA's component. So the order is 4, 1, 2, and then this is basically the seasonality components. Okay, and the kind information criteria are this one. So using this particular model, we are forecasting for the next 30 time periods. Okay, so that is dot predict, and then we are plotting this one. So I hope you have got the idea how we can apply the exponential smoothing methods as well as ARIMA methods, simple one, as well as with the seasonality factors, and how we can apply the moving average methods using Python. Thank you so much. See you in the next.